Okay, let's talk about DeepSeek.
Welcome, everybody, to Product Management Exercises community sessions for our AI Product Manager program. If you haven't already taken our learning program, the link's in LinkedIn. I'll share it here in the chat. Um, Please join us. Corey is one of our instructors, as is Kai from Uber, and you can learn about AI product management and how to elevate your career. We'd be very excited to have you. Our next cohort is in April, so I'll put the link in there. And yeah, without further ado, this week DeepSeek came out, and I think shook the industry. So a lot of new information has come out, and Corey has been kind enough to do a deep dive and will share a lot of information with us, and I'm sure we'll have time at the end for a lot of questions. So on to you, Corey. It's all yours,
Well,
and
thanks,
thank you for doing
Ida.
this.
Yeah, of course. This is obviously a very exciting topic. And first of all, I'm excited. I see a lot of names that I recognize from past sessions in the crowd here. So good to see your faces and names again. So that's exciting. But yeah, um, DeepSeek, I'm going to do as much of a deep dive as the week of news allows and how fast things are changing. I was editing slides, last night and this morning as new insights kind of arose. So I'm going to do my best here. But before we get started, just for those who I haven't met before, a really brief intro. Corey, I'm a product manager. I work on technical products, mostly in the applied ML space. At least that's where I got my career start. I then worked on LLM infrastructure, dev tools, getting things into production at Google. I've worked at a startup doing AI coding assistance. I now work on model eval at Amazon. This talk, though, is strictly my point of view, or I should clarify that. It's an aggregate view of a lot of people that I trust, and with a little bit of my own kind of opinion interjected in the middle. I do my best to cite my sources here from, so that you can go and kind of read the source material where I'm getting some of these insights. And definitely nothing that I'm talking about reflects the views of Amazon or prior employers. It's not intended to reflect potential changes in any strategy or anything along those lines. These are kind of strictly my own views. I think the second disclosure is things are moving really, really quickly, both in AI space as a whole, and certainly with what we know about DeepSeek. And so I try to acknowledge uncertainty and competing views where they exist, which is many of these places. And so I'm trying to offer up information for you all so that you can make your own kind of informed opinions about where things are going versus stating, one big set of facts. What are we going to cover today? So, I like to assume here that we're coming from kind of a mix of backgrounds and not everybody, maybe has like spent their whole life thinking about LLMs, or at least what feels like a lifetime for me. So I'm going to give some context just briefly about why we're talking about the subject. What is DeepSeek? What was announced? Why do we care about this? I'm going to take a step back. I'll talk a bit about some key trends in the AI industry that are important for contextualizing like the importance and the ramifications of DeepSeek. We'll do a little bit of like a technical dive into a few of the core technical components of the DeepSeek papers, of the three models that were released. That way we can understand like where the state of the art is progressing. We need to know some of those foundational concepts. Then we'll like wrap it up by saying, okay, what are people talking about? What are we excited about? What are some of the future implications? And I'll leave us with some questions to think about, and then we can hopefully open it up for a discussion there at the end. So as I had mentioned, it is a lot of material. I'm going to move relatively quickly. So, please bear with me, at least as we get into the, through the technical stuff, just so that we can get to those questions at the end, which hopefully we have a rich conversation. Yeah, with that, let's go ahead and maybe instead of doing like live questions, if you can post stuff in the chat, I'll do my best to kind of read those and respond real time. But I can't promise that I'll catch everything. But Ida, if you see something that's stands out, let me know, and I'll try to stop my rant. Okay, let's get right into it. So why do we care? It's really hard not to have been inundated with DeepSeek news the past 7, 8 days here. I think for those of us like in the technical space, this is something that we've been paying attention to since the end of last year when the DeepSeek v3 paper came out. and certainly just is part of the onslaught of just continuous improvement that is happening in the space. And this really marks some interesting changes where not only has the state of the art advanced, but we've opened up new fronts where we are pushing now on different areas that we might not have necessarily been pushing on quite as much. So the incentives have changed a little bit as well. But for people who are not maybe as necessarily technically involved in like LLM development and getting these things into products, if you have any sort of investment in US tech stocks, you certainly were shocked to wake up, I think it was on, Monday, and see, Nvidia down 15% or something along those lines, aggregate indexes down 5, 7, 8%. So at a minimum, if you have any money invested, you cared about this. And certainly that's what drives a lot of the mainstream media adoption of these types of stories is, something is going on here, let's talk about it. I will say this is strictly my opinion, at this point, a lot of the initial reaction was overblown, at least in terms of how markets reacted. And I think that we're seeing that correction already happening, where people are starting to, digest the material a little bit more thoroughly and are mitigating or kind of pulling back on some of those initial reactions. But we'll talk about like why I have that opinion here. But nonetheless, it was a really interesting advancement and something that we should be paying attention to, and we should be having this conversation. So quickly, like just primer, what is DeepSeek? So DeepSeek's actually been around for a lot longer than last week, and it's been around a lot longer than the end of last year. I mean, a lot longer in the scale of LLM research labs and things like that. It was founded in 2023 in May. It's actually born out of a hedge fund called Highflyer in China, which is a quantitative trading firm. They spun up an AI research lab as part of that quantitative trading program, and then they got into the LLM space, and notably they got into the open source LLM space. So they were training open source models. This is very similar to what Meta does with their Llama series of models. And they had a couple notable releases actually through 2023 and 2024. In November 2023, they launched a model called DeepSeek Coder, which at the time, really no one paid attention to unless you cared a lot about AI coding, which I happened to at that point. And DeepSeek Coder was one of the models that when I was at SourceGraph, we used DeepSeek Coder as part of our autocomplete offering. So this would be something that we would use to generate, very fast and reliable auto-completion of code while people are typing and do things like that. And so what was really interesting about the models is they were very fast, they were very good, but they're hyper specialized at coding. So they didn't have quite the big splash that some of these more recent releases have had. In January of 2024, they kind of released their first mixture of expert model. I'll talk about what mixture of experts is. It's not a novel concept. It's been around for quite a while now, but they released DeepSeek mixture of expert, which actually showed some pretty good gains in that space. And we'll talk about like what some of those gains were, but really it boils down to mixture of experts are efficient for inference, but they are complicated to train. They made some progress on making them easier to train, which was a nice step forward. And then obviously most recently in December of 2024 and this month, they released 3 new models, DeepSeek V3, DeepSeek R1, DeepSeek R10. And that's what we're going to be talking about because all of those pushed the state of the art in their unique areas. So let's talk about some trends. What is the context? What is the environment in which these models are being released? So this will be familiar to anyone who's really, started to read about large models. There's this notion that we like to call scaling laws, and it's quite important for the macro picture of what is happening in AI research and in the labs. And really it boils down to this very novel or like very basic concept, which says if we apply more data, if we apply more compute, and if we make bigger models, they get better. And they get strictly better. And they get better in a nearer, or in a very smooth fashion, I should say. So it's very predictable to say if we add this much more data, if we make the model this bigger, if we add this much more compute, we will get a model that is better on some set of reasoning or some set of kind of computational tasks and things that we would want these models to do. This paper, I can't remember, is called Scaling Laws. I link it here. It came out, maybe 4 or 5 years ago at this point. There have been a couple other papers released, Chinchilla Scaling Laws from Google and some others that kind of extrapolate this idea a little bit further and refine it. But the core idea is still the same. It's like all else equal, and this is a nice quote from the CEO of Anthropic, Dario here. All else equal, scaling up the training of AI systems leads to smoothly better results on a range of cognitive tasks. So what does that mean for the industry? Well, this is what is driving those massive investments in compute that we are all kind of hearing and is trickling out into the media. Well, we're investing in more data centers. We're investing in more chips. We're investing in more data acquisition. This is all the natural logical flow of scaling laws where we say bigger is better. Oops. So the scaling law really gives us this function that just in the most simplest terms, it allows us to take dollars and turn them into intelligence. And the only limiting factor is, can you turn those dollars into the intermediate state of infrastructure? And that is what everyone has been racing to do. And so, as I mentioned, kind of the logical conclusion to scaling laws is put more money into things if you want a better model. And so we see this with massive investments in capital spending across the major the big 5 tech companies who are involved in this space. Obviously, this is ignoring venture capital funding that is going into firms like OpenAI, which just announced that they're trying to raise, I think, another tens of billions of dollars at a $340 billion valuation. So there's a huge amount of money sloshing around here, and it's all purely trying to turn that money into intelligence. And just like if we look at data center growth, it's nearly doubled the number of data centers over the last 4 years. So large amounts of investment, all in the name of scaling laws. And chips are the forge here. So as I mentioned, like in the data center, right, we need chips, and there's clearly one major provider of cutting edge chips, that's NVIDIA, and that's obviously why we've seen such a large increase in NVIDIA's stock price and underpinned by their revenue. I'm not going to talk about what the valuations here. I'm not going to get into like if this is overvalued or undervalued, or if there are other competing things, and what is NVIDIA's moat. Those are all great questions, but just accept that a lot of chips are being purchased. And of course, other companies are investing in their own hardware. Notably, Amazon has Trainium chips. Google has TPU chips. So there are non-NVIDIA comparators out there. Mostly, though, scaling laws have been applied to the foundation model. And so if you've taken our AIPM course, I talk a lot about the difference between foundation models and derivative models and things along these lines. But the foundation model really is kind of these core intelligence models that are being released. Your GPT-4os, your Claude Sonnets, your Claude Opus, your Llama 405B, like all of these very large primary models. And we have really been focused on scaling those up in both the size, the amount of data, and how good those models are. Those models also have a just absolutely enormous amount of cost to train. I think that we started, when we were initially training these models, people's eyes started to water a little bit when we were talking about $1 million to train a model. I think that I just saw some analysis that is saying, we're very much on track for $100 million training of frontier models at this point. So enormous amount of cost going into training those models. Now, a dynamic that's important to know is that once the model's been trained, the cost to run inference on that model, i.e. make predictions, is relatively very small. Even for the large models. It can be complex, but it's relatively minute. And that's why the actual cost that you pay as a customer of one of these companies is not too high, I should say. Now, obviously, some models are more expensive by orders of magnitude than others, maybe $10 per million tokens versus $1 per million tokens, or even cents per million tokens of output. But most of that is fixed. So you're not, depending on what you need, you pay the same amount for every inference call that you make, as long as like the fixed on tokens. So fixed on the length of the text going in, you just kind of pay a fixed amount coming out. The complexity of the question doesn't matter, is another way of putting this, right? The model is as good as it's going to be. You pay just for the answer. But there's been the shift to what we call inference time scaling. And so scaling laws are, and this is kind of the concept that I'm going to try to land here later. They can exist on multiple fronts. So we've talked mostly about how scaling laws have driven investment into the foundation model. But there are lots of different areas where we can achieve scaling by spending more time and more money and more inference. And that's mostly been on the foundation model. But in the last year, we've actually shifted to this paradigm where we're spending more money on inference time compute. And so the difference here is, instead of spending time training the model more, which we still are doing, to be clear, we are now putting more money into multiple inference steps. So instead of just paying based on the number of tokens, you might actually make multiple calls to the model to get to the final answer. And so this actually, like, this makes a lot of sense if you think about how you think, which is not you just regurgitate the first thing that comes into your mind, right? When someone asks you a question, you might make an assumption, state that assumption in your head, refine that assumption, think about the implications of that assumption, refine it further, and then you might finally give your answer out. Well, each one of those steps of kind of stating an assumption, thinking about the implications, refining your answer progressively is something that we can do with these LLMs, but it means multiple round trips to the model, multiple API calls. And so in where it used to be just one return, one round trip, now it might be 10, 20, 30, hundreds or thousands of round trips to answer really complex questions. And therefore, the amount of investment in this inference time scaling is growing. And this is opening up a new front in terms of scaling laws for us. And we actually, like, the most notable release actually came at the end of last year in December from OpenAI. And what I'm showing here is a chart on what's called the ARC AGI prizes by Francois Chalet, who had worked at Google, now he works kind of on this project here. And it's not a complex task set or challenge for humans, but it's a really, really complicated set of problems for LLMs. And they're kind of geometric reasoning problems, things like that. Think like Mensa sort of tests. And they take a lot of reasoning to think through. And so what we saw is that by scaling up, you have better models here. So like O1 Mini is a smaller model than O1 Preview. But then as they scaled up the amount of dollars they spent on the task itself, so in thinking time, you actually got significantly better results. And so that's another key finding that predates a lot of what DeepSeek, but explains some of what DeepSeek was investing in. Okay, I'm going to take a quick pause because I saw a bunch of questions, and then I will see if I can answer some of these. So DeepSeek disruption, what it delivers. Okay, I'll cover that later. How do scaling models or scaling of models correlate with scaling of AI chip hardware? Just to understand relatable terms. Okay, yeah, that's a good question. So you can think about things in a couple dimensions. So one is the number of chips required to hold a model or kind of run a model in simple terms. And so as models get bigger, you need chips that have more memory on them. And if you think about kind of the core operations that happen in model training, there's really, like, I call it like turning the crank on data or operating on data. That's like your compute. And then accessing that data so that you can turn the crank on it, that's having your data kind of right near your computation center, and then moving data around. So like you can't necessarily have all that data on hand at the moment, so you need to have it somewhere else in your data center, and you need to move it onto and off of these chips. And so there are kind of three things that are important here. Is how much raw compute do you have on the chip? The more you have, the better. That's true. Then the more data you can have close to your computational center of your chip. So this is like, think about this as RAM, or kind of like very quick access memory. That's really important, because if you're spending time going to a slow memory bank, then you waste a lot of time in training and things can take a lot longer. And the other thing is like network interconnects between chips. So all of this training happens in a parallelized format over many, 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 many chips. But the faster we can allow these chips to talk to each other, the more they can act like one big single chip. And so this is what like NVIDIA talks about a lot. So those three things are really important. And so as we try to scale greater and greater models, we need more compute, more RAM, and faster communication between chips. And that's what gets delivered basically on a rolling basis here, and why the average lifetime of any given chipset and kind of like data center configuration might be at like order of 8 months or so before they're kind of getting reconfigured. Okay. Domain specific, maybe. Okay. I see a question about like domain specific things. Scott, I'm not sure what that was specifically talking about, but I do agree, like generally we get NLP right, but actually, yes, there is additional tuning of these models. It's not purely scale. There is additional like third stage, second stage training that refines domain specific actions. We're not going to really talk about that too much. I don't know the difference between frontier and notable models. I haven't heard notable model before. And then concept and importance of distillation. I'm going to talk about distillation. Data to model parameter ratio. Okay, yes, I don't know off the top of my head, but there is kind of if you look up the scaling laws paper, they basically have a function that says, given a certain amount of data, how many parameters should you have? There's a bit of a correlation there. It's dependent on a lot of underlying factors as well, like the exact architecture and algorithms that you're using and things like that. But they're kind of rough guidelines that if you have certain trillion tokens, you're going to need certain billion or hundreds of millions of parameters. Okay, technical concepts. Just briefly, so that everyone's on the same page. And Scott, this talks a little bit about, and I know that we've covered this in the PM class before, so you're familiar with this, but there are a couple different stages of training. They all yield different benefits to the model. Pre-training the model is, what we do with the vast quantity of information that we skim off the internet. And this is what everyone's doing, and everyone basically has access to roughly the same data at this point through scraping methods. And so really what it is trying to instill the understanding of language, is trying to instill general capabilities about connecting language and some basic reasoning skills and a lot of world knowledge. This is what happens in pre-training. Basically what we're doing is like predicting the next token in a sequence, filling in a gap in a sequence. It's a very scalable way of training a model. And this is what results in what we call the base model, not to be confused with a foundation model. But the base model is just like this model that is potentially really good at filling in the next token, but it wouldn't answer a question in natural language from you really well. It's not going to follow instructions really well. It's not going to have a lot of domain expertise, but it will do a really good job just filling in a token. And in the weights of that model, there's a lot of really interesting kind of emergent behavior that we then extract with these other training techniques. Supervised fine-tuning is where we actually apply lots of labeled data to the model. This yields a model that is a lot better at kind of following instructions and patterns of behavior and interaction with humans. Reward modeling might be something that we do to kind of get the model to be really good at a certain task. And this is similar to reinforcement learning, where we're going to actually give the model direct feedback from its interactions with humans or with other kind of AI systems that are giving it feedback. We call these kind of grader models, or kind of AI as grader models, or AI auto evaluation models. And these models give feedback to the model on its answer, and then it modulates its response to get better alignment to how we might want the responses to look and feel. So it's really starting with nothing, adding world knowledge, adding general capabilities, refining those capabilities, aligning it to the kind of outputs that we want, and then really kind of putting the final polishes on it. And these are the 4 major stages of training. Very quick overview. Reinforcement learning is really important, and it's not something novel. It's obviously reinforcement learning as a class has been around for a very long time, commonly seen in robotics. The core concept here is that we interact with an environment, or we interact with some sort of external system. And that system is going to give us some information about how well or not well we did on whatever this arbitrary task is. So in robotics, this makes a lot of sense. If you're trying to drive a robot down a maze. Did you bump into the wall? Yes. Okay. Feedback. Did I bump into the other wall? Yes. Feedback. Adapt your mechanism using that reinforcement learning. And it doesn't require you to get all the way to the end of the maze, if that makes sense, before you get your feedback. You get these interstitial bits of feedback. Well, we can do this for LLMs as well. And so instead of training the model with here's an input and the perfect answer, all we have to do is say, here is the input, you give me an output, and then I'll tell you if it was good or bad. Okay, so that was like the first thing that we were doing with reinforcement learning here. And there's a method called direct policy optimization, which is basically you literally put a bunch of outputs of a model in front of humans. They give a thumbs up, thumbs down, and then you use those thumbs up and thumbs down to go back and reinforce or update the model weights. Then we kind of adapted that and we said, well, it's not scalable to always put the outputs in front of a human. So what we're going to do is actually we're going to train another model on human labeled data, thumbs up, thumbs down, to approximate what humans like. And then we're going to use that approximation model to then interact with our primary model. And then they can go back and forth together at a much more scalable rate to improve the alignment of the core kind of original model. And this is what we called kind of our like reinforcement learning with human feedback, reinforcement learning with AI feedback. These are all kind of the same things. And you have this proximal policy optimization PPO cycle here. That's what a lot of RL was doing. One of the key insights about RL is that it tends to be really unstable if you just use it in what we call kind of the naive state, where if you don't have this like AI model that's representing human feedback in the loop, it's really hard to get the model to converge on anything good if you're really just relying on like some sort of other hard-coded, not kind of human feedback type of reward signals. It was really hard to get this to work. So we spent a lot of time trying to make these reward models, these second order models train really well and kind of build this loop. But it's computationally expensive because now you're training multiple models. It slows down training time. It's complex to implement. There are a lot of things that are challenging about RL. The other thing to know, like terminology, chain of thought reasoning is also been around for quite a while, but basically the idea is thinking step by step instead of just giving the first answer, right? And so the first kind of instantiation of this was we would just prompt a model to think step by step. Literally, I remember we would say like, answer this question and think step by step. And because these models act recursively, generally, they would first spit out their interstitial kind of thoughts before arriving at the final conclusion. But we were doing this all through prompting. And then there's like this realization that, well, actually what we can do is we can take a bunch of chain of thought data, literally thought processes and final conclusions, and then we can train the model directly on those. So we can give it an answer and a bunch of chains of thought that are manually written by humans, experts, annotated by, in a lot of effort to kind of write these things out. And we can then train the model directly on that data, but very, very expensive to get that data and to do it at scale and to do it across the amount of domains that these models might be used for. So very challenging. But by doing that, training with chain of thought data versus just prompting, this is what led to a lot of the great reasoning capabilities that we've seen with models like O1. Now, I'm probably way oversimplifying all of the other sort of things that go into making these models great for reasoning, but this is kind of the core concept is, can you train it to logically think really well and do that through labeled data? You can also do RL for chain of thought. So instead of strictly feeding the model labeled perfect chains of thought, you can actually have the model predict different chains of thought, and then you can construct reward signals that, based on their reasoning steps, it promotes certain chains of thought versus other certain chains of thoughts. And that has tended to still require us to have humans in the loop, or humans, providing annotated data to allow us to compute those reward signals. And so it was still expensive, but it did allow us to kind of start to use RL in this chain of thought space. I'm going to take a brief pause. Okay, DeepSeek refusal on certain topics. I'll talk about that. It doesn't have. Okay. Yeah, doesn't seem like any questions. Mixture of experts model. The way to think about this is there are two pieces of terminology. There's dense models and then there's sparse models. And these are kind of important concepts to know. A dense model is a model that activates all of the parameters in the model every time you run inference. So if you have 100 billion parameters, you are activating 100 billion parameters every time you're running inference through that model. And so the computational cost of generating inference is proportional directly to the amount of parameters in that model. And it's high. A mixture of experts was this idea, and not something that DeepSeek launched, but it basically said, hey, not all parameters necessarily are needed to answer every single question. That kind of makes intuitive sense. So is there a way that we can force the model to only use the parameters that are necessary for answering the question at hand, and therefore not have to spend the time doing all the computation for all the other parameters? And this is what mixture experts was, or is. And basically it uses what we call a gating network, or kind of a sub-component of the architecture to, quote unquote, look at the incoming question and then route it to a sub part of the network to activate that sub part of the network. And so you can have a 600 billion parameter model that behaves like a 100 billion parameter model or something along those lines at inference time in terms of how much compute it costs. So it allows us to have a much, much larger model, better for scaling laws, but only use the segments of the model that we really want. The complexity here is that mixture of experts are much better at inference, but they're very, very, very hard to train. And one of the kind of key things that we realize, and I'm using we very liberally here, like I'm not involved in a lot of this, but one of the things that was understood was mixture of experts models tended to like converge on using only a few of the experts, and it would kind of ignore a lot of the other experts. And it was very hard to get it to balance equitably across all these experts. So you ended up with a lot of wasted space, to put it simply. And so they were very complicated to train in a balanced way. And so there was kind of this spike in usage of mixture of experts and then more of like a convergence on dense models later. Yeah, it's kind of like a sorting algorithm. Yeah. Or like, I think if you take the class, we talk about like model routers, like an application space, where we're like, hey, use a big model when you need a complex thing, or a small model when you only need an easy task. It's kind of like the innately defined version of that, where all of that happens like internal to the model itself. Okay, let's talk about DeepSeek. 3 things were released. DeepSeek v3, December last year. DeepSeek R10 and DeepSeek R1. V3 is the foundation model of this family. So no real chain of thought, no reasoning capabilities, limited RL, if not no RL. It's a mixture of experts model, 671 billion parameters, but you can see that it only activates 37 billion per inference. So you're getting like, over a 10x reduction in number of parameters used at inference. So really good model. And it also was competing with state of the art at the time. So Sonnet 3.5, GPT-4o, models along those lines. It was competing with that, though it was released, many months after those models. DeepSeek R10 is, from a technical standpoint, potentially the most interesting model that they released. This is a derivative of the V3 base, and it uses RL without any supervised fine-tuned data. So this means that we did pure RL without having to go and get all of those chains of thought, human annotated data. And additionally, it doesn't use an additional AI model to interact with this model during the RL state. So eliminated the complexity of the additional RL model, eliminated the need for human annotated data, but still came out with a model that was really, really good. So that's really interesting. Now, a couple notable things about like R10. They claim that the model thinks really well, but it does other weird behavior that like from like a pure user standpoint would be undesirable. Like it mixes languages. So it'll like use English and it'll use a different language in its responses, even if the logic is sound throughout. And it does other sort of weird behaviors because it lacks this fine-tuning data and like some of the additional refinement that we normally do. It doesn't have this like polished output, but it reasons really, really, really well. And it did that reasoning really well without having to have labeled data. So that was like the amazing insight. Like take away one thing, it's, oh, we don't need to know, we no longer need a lot of human annotated data in this complex like policy model setup to get strong reasoning. R1, they basically did they took zero and you did a bunch of the SFT stuff and they put a bunch of other kind of traditional RL on top of it. And now they have a reasoning model that is as good as O1 or kind of other models. And I'm saying as good as like, is approximately as good as, depending on how you look at that data. The key thing here is it's open source though, so it's free. Now you can go and pay DeepSeek for inference and API calls, but you can run this on your own hardware, and you can access it for free, and anyone can kind of host this model. So really interesting there. So, oh yeah, they released a free app. It's the #1 as of yesterday in the App Store. A lot of demand, obviously, from China, but huge demand from US and other as well. And this model basically, one thing to note, I kind of make this distinction in the PM class a lot, is like models are not the same as apps. So don't conflate the two. ChatGPT is not GPT-4. ChatGPT is not O1. DeepSeek AI Assistant is not R1. It likely uses R1, but they're going to build a bunch of stuff around R1. And so I saw some comments being like, hey, it deflects certain things, it's censoring itself, like whatever. Yeah, that doesn't mean that the model itself will be censored or deflect. I don't know that to be true. Like I haven't run those evaluations on it, but they definitely are going to put safeguards around that model in their application that are going to be doing some sort of pre-post filtering and amongst other things. Okay, let's just back up some of the statements with data. R1 competes with state-of-the-art soda. This is directly from their paper. I really highly recommend you go read the R1 paper, and I really highly recommend you read the V3 paper, which came out in December. If you're interested about these things, it's a wealth of information. And so you'll see that like on these 6 different tasks, which are some of the most complicated reasoning tasks that we have. So these are like, when we do evals over potentially hundreds of different benchmarks that we care about that are all kind of trying to tease out how good a model is at something, broad or something very specific or deep or whatever. But these 6 are kind of the leading open benchmarks that require a lot of complex reasoning. One thing to note is that not all questions require reasoning, and just because you reason well doesn't mean you're going to be good at things that don't require reasoning. And so things that reason well are types of questions that you can logically derive an answer. So write me a poem does not require reasoning, and a model that's really good at reasoning is not going to write better necessarily. It's not going to necessarily have better world knowledge. It's not going to necessarily know more facts. But if you give it a math problem or a coding problem that can necessarily be broken down into logical steps to arrive at a conclusion, it will do better on those. That's what the reasoning model strength is. And so that's what these benchmarks test. So we have basically math, code, like professional exam, math, language reasoning, code. So a lot of similar things. And you can kind of see, better than O1, near O1, better, kind of close, better. So very close to state of the art, which has been O1. Notably, though, this is different than what OpenAI released end of last year, O3, and they're not using this kind of infinite inference time budget that pushes reasoning models into like the stratosphere in terms of their capabilities. These are kind of standard API calls being made here. So these are kind of direct comparisons, but we know that we can get better if we run more and more inference. So if we really open up the floodgates at inference time. This has been proved, if you don't trust DeepSeek, which some people don't, it's been proved by other people. So this is artificial analysis. Check out their website, really epic. And they're very fast at getting evals up on the board. They've confirmed most of the numbers. Okay, so how do they actually train these models? So you'll see down at the bottom, there are 3 different variants. There's the 0 model, there's the R1 distilled models, and then there's the R1 model. And we start with V3 base. So actually, a lot of the technical advancements that they made happened in the V3 paper when we're talking about like network infrastructure, data manipulation, chip hardware optimization stuff. That all happened in V3 and is super, super impressive. But it all happened in V3. A lot of the RL advancements and the algorithmic changes is what happened in R1 and R10. The basic thing is what I told you, earlier, which is taking V3 base and then following this dotted line to R10. The only thing that they had to do to get a very good reasoning model was they ran what's called reasoning oriented RL or GRPO. And this is basically saying we can have these rule-based reward systems. So not another large model that has been trained specifically to provide reward feedback, not human annotated data that is used to derive feedback, but just strictly doing RL on the reasoning steps. We can compute a really good model. The actual mechanism that they use is they produce, for every input question, they produce n different chains of thought and answers from the model, and then they compare those produced chains of thought against each other, and they can do that algorithmically, and they can kind of optimize, they can find the ones, and you can kind of think about this as like voting for the best path. That's not necessarily like the mechanism, but they're kind of like looking at all of those different chains of thought, and they can then use that tied with the known answer to enforce better, higher quality chains of thought. And that is really like impressive, really impressive that they were able to do that. A lot of other models would what we call kind of collapse in that paradigm. And then DeepSeek basically is the same thing. Forget all this interstitial stuff. It's cool. Go read the paper. They create a lot of data. They use the models to create other data. Then they refine that data and they cull it and they like annotate it and they do a bunch of like interstitial data creation and things. But basically they add supervised fine tuning and like traditional RL and they get R1. But they do it, this is kind of the key insight. The other thing that they describe in the paper, which is really interesting, is like this aha moment that happened in their mixture of expert training, where, or sorry, in their reasoning steps, where without like prompting the model, they can actually see the model dynamically think about how good its outputs are. So, like put in the most simple terms, if it generates a chain of thought and it quickly gets to an answer and it says, hey, this answer seems right, it stops. But if it generates a chain of thought and it's like, I don't think I have the right answer, it keeps going without having to be prompted to do so. And it can actually figure out how much reasoning, how many kind of chains of thought and kind of recursive interstitial ideas it needs to create to get to a really high quality answer without having to be prompted to do so. And so that's actually a really interesting, finding as well. Okay, I want to make sure that we get to questions here. So there are a couple different types of RL that they use. I think we talked about those. One basically is not using a model, and one is more traditional using of a model. I highly recommend going to read the paper. The balance there is interesting and insightful. There are a lot of optimizations as well. So this is mostly from the V3 paper. They spent a huge amount of time, and this is where some of the geopolitics start to come into play. DeepSeek, in theory, doesn't have access to the latest chips. And so this is kind of one of the big points of debate. So they were forced, the chips they have, H800s, it's a Hopper GPU chip from NVIDIA. It's not as good as H100s. And it's not as good because it has slightly less memory and it moves data around more slowly. It's the basic way that they nerfed these chips. So they spent a lot of low-level time programming these chips to optimize communication efficiency, computational performance, memory optimization, and things along those lines to squeeze everything they possibly can out of these chips. Whereas most teams might just say, hey, NVIDIA probably in CUDA, the low-level programming language, has done the best optimizations that they can. We're just going to take that at face value and start to build with it. They went way deep to try to squeeze out value, and that's where they got a lot of training performance. They also found a lot of model efficiencies. We've talked about some of these. There are, a bunch kind of listed in the paper, but the key takeaway is that they were able to figure out cheaper ways of adapting their algorithm so that for the same amount of data and the same amount of compute, they got a better model. So when we talked about scaling laws, now tying it all the way back to the beginning, think about this as shifting the curve. Okay, so it's not we're progressing along the curve by adding more and more. We're shifting the curve. This is also not new. Everyone shifts the curve. Everyone is investing in more efficiency, but this was a bit of a step function improvement that we might have expected other people to get to eventually. But the fact that they did it out of necessity and they open sourced it are kind of the key things. And so it shifted that curve. Um, the other thing that they found out is they can transfer this intelligence to other open source models. And so one of the things that's really interesting is that they can actually use DeepSeek R1 to train other open source models like Quen and Llama and get really, really high quality models. So you bump, like if we just look at, Llama's performance here, if you use R1 to train it, it now gets better than GPT-4 at most of these tasks, whereas before it wouldn't have been as good as GPT-4. So now there's this feedback loop in the open source community where a lot of these models can like now quickly build off of each other and get better and better and better. Okay. Key takeaways. I'm going to try to wrap it here in 3 minutes and then we can do discussion. RL can teach reasoning alone. That's big finding number one. Finding number two is we thought we were doing a good job at getting more efficient. There was clearly a lot of headroom and probably exists a lot of headroom and efficiency. And so a lot of labs are going to be thinking about how to do efficiency more. They're probably investing in efficiency more than they were before this. Open source now rivals state of the art. Before it was always pretty close, but not as good. Now it's as good. Does that exist forever? Who knows? But I think the key takeaway is it now is as good, and it can quickly get as good as kind of the leading state of the art. So we're opening up new frontiers on new RL investment. So instead of just purely looking at foundation model scaling laws or inference time scaling laws, now there's this new frontier of RL, very under researched, under invested space. A lot of money can go in here. A lot of compute can potentially go into RL to scale RL capabilities. We're shifting the scaling law curves so we can get better models for cheaper. And a lot of those are going to be freely accessible. So what's the big deal? Just quick cutting through the noise that might exist. No, they didn't train it using $5 million. That's like they were pretty clear about that in the paper as well. They said the final training run costs $5 million. That is nothing related to the real cost of training the models. For instance, semi-analysis indicates that they've got 50,000 Hopper GPUs, which would cost $1 billion. So they've got a lot of infrastructure at play, and they're using that. And so the final training run does not take into account all of the experimentation and data creation and curation and salaries and all of this stuff that goes into training these models. So it's still very, very expensive. The other thing that Dario will say, I'll get to that. So yes, they are limited in chips. They have access to, but we don't really know. There's a lot of debate, like, do they have H100s? Do they not? Do they do this purely on H800s? Nobody knows, I think, is the takeaway at this point. Let's assume for face value that they did more with less. Exactly how much less, we don't really know. Yes, they made a lot of performance gains. Super impressive. We should pay attention to that. No, it doesn't necessarily. It's not like some out of the blue, no one was thinking about this shocker. Dario from Anthropic did a lot of napkin math. Caveat, obviously, he has a vested interest in kind of saying, yes, we also thought about this. But the math basically checks out, which is given the average rate of efficiency gains that we've seen over the last 5 years or so, given that this model is as good as models that were released, 8 months ago or so, if you extrapolate where our efficiency was at 8 months ago and you extrapolate that today, yeah, we start to buy the, $5 million final training run number. So it's not like something like they did a lot of great work, but it wasn't some like massive acceleration in one direction per se. But that doesn't mean anything that we should take anything away from the work that was done. It's uncertain if they use other outputs from models like GPT, like Anthrop or OpenAI's out there saying, oh, they used our data, they ran inference on GPT models to then train their model. We don't know if that's true or not true. There are a lot of geopolitical and just political reasons why people are arguing about this. It actually doesn't matter, is the short of the story. because that would have a relatively negligible impact on some of their work that they did in the RL space. You traditionally, when you use inference data from other models, you need the logits, or like the predicted probabilities of all the tokens, to really squeeze a lot of training value out of it. Just having the raw data, it's not like that interesting. It is valuable, so like yes, they could do it, but they've already done it, and this model, that's data's out there one way or the other, and other people are doing this for sure. So it's not like, oh, they cheated somehow, and it's like they'll never be able to replicate this again. So 3 questions for us, like, and this is a lot of like what the market was thinking about. Does a drastic improvement in training efficiency mean that companies are going to spend less on infra? What incentives do labs have to invest, significant capex if a free version of an equivalent model comes out a few months later? What will pricing pressure do to margins of companies like OpenAI and Anthropic and others? And is China somehow beating the US in the AI race? Should we do something? I don't have answers to these questions, but this is kind of like what's driving a lot of the discourse right now. My thoughts are just generally, rising tide lifts all boats. This is open source. Everyone's going to take advantage of this. We're going to see really rapid adoption. Expect that llama models accelerate quickly. We've already seen Qwen models released this week that are much faster. Expect that everybody takes a lot of these efficiency gains and builds off them. Intelligence isn't a fixed goal. It's not like, oh, we either have reached the end state or we haven't reached the end state. I know that there's like AGI talk, let's forget that. But like, we're trying to make better and better models. Having more efficient things means that we can put more money into that forge and get more out of it. So people probably will continue to spend on infra, and the companies that have a lot of resources are going to put a lot of those resources into now a more efficient system to get a more intelligent model out. So I think that there is going to be continued expenditure there. People might review their capex, expenditures and things like that. I'm sure that's happening, but I think this is more of an accelerant than it is a decelerant. Models will get cheaper, and this is really good for builders. Like if you're out there thinking like PM, we already have really amazing models. They're only going to get cheaper to use. And because of that, I expect more building to happen and inference demand will accelerate. So if you're a company that sells chips for inference, this is a good thing. NVIDIA sells chips for inference. So, the training is only one side of the coin. Don't forget the whole picture here. More demand, better AI, more AI leads to more demand for these chips, all things considered. All right. That's really rapid fire. We got through like a huge amount of stuff. Let's open it up for questions. I don't know if you want to like moderate this section.
Yeah, absolutely. We can open it up for hands up, and then you have some in the chat. I don't know, Corey, if you want to go through those, but Harsha's raised his hand. Harsha, do you want to go ahead?
Yes. Hi, Corey. I remember your responsible
Yeah.
AI into the course. So
yeah,
nice
good to see you.
See you again. So my question is that Alibaba yesterday announced a new set of models which says is better than DeepSeek, and
Yeah.
they've done multimodal and the operator kind of a thing. So why didn't Alibaba's announcement have the same waves and disruptions like DeepSeek did? That just looks like a little byline to me, but I don't think a lot of people are talking about it.
Yeah, that's a good question. I don't have an answer to that. I saw the announcement. I think it's probably because everyone's already reacting to like there's only so much capacity to get worked up about things is probably the answer. Anything else that I could say would be speculation. But this actually dovetails into Corey's question about why do they spend so much money and then open source it. There are a lot of reasons, like motivations companies have for open sourcing things. One motivation within China or just basically non-US firms might just be to bolster non-US tech. And so you're going to see, I think Alibaba, Quen, like you're going to see like a lot of really fast adoption of this stuff. So let's expect that everybody has a model that is incrementally better in the next months and weeks, things like that.
Ida, can I ask a quick follow-up question, please, if that's okay?
Yeah.
Can I have
Of course, go ahead. Yeah.
So in the realm of small language models, right, as compared to large language models, where do you see the competition going? I mean, will something like a DeepSeek go and disrupt these SLMs too?
Yeah, probably a lot of nuance there. You need large models to get small models. So small models are always derivatives of large models. So advancement at large model yields better small models. So that's one paradigm. Small models are better for, or small models are already better than what we need for a huge amount of tasks. And I usually talk about this as like development runway that we have. I think that, of course, frontier models advancing opens up wildly new doors. But we like in the world of enterprise ML, which tends to be pretty not sexy, and the amount of like actual ideas that we have for how do you incrementally optimize business processes and things like that, there's a lot that we can do with the existing technology. And small models are the way to go there because they're going to be so cheap. And I think that what we're going to see is small models get increasingly good and that puts downward pressure on. And so the kind of marginal costs of doing this AI start to drive towards, not quite zero, but near zero, which is the trend that we saw with like general compute and general storage and things like that. So I think that that's like definitely the way of the world. Yeah, Scott, I
Thank
saw
you.
the question in the chat about like the speculation that they had a short position. I think that that's speculation at this
Yeah,
point. I think,
I tried to verify. I have not seen anybody show any proof of it. I think that's just sort of people being people. I'm just saying that
yeah,
it's one
yeah.
theory. That's all.
Yeah, I think it's probably like I buy into this concept that there's a general interest in not having one or two companies dominate the whole future of this space. And certainly people have added like incentive to not have it be one or two US companies. And so just having a competing open source alternative is advantageous in some geopolitical space. Now there are other like Meta has other reasons for wanting to open source, and we can talk about those and things like that, and whatever. But
Well, I mean, I'll tell you from a product management perspective, insofar as sometimes PMs also have P&L responsibility for products, which isn't always the case. Sometimes we're feature factory people, sometimes we're technical product managers, but sometimes more general. The idea that inferencing costs can go down drastically, and that was part of an article series I wrote about search in general and how it impacts search. Because
yeah,
search indexing is fractions of a penny,
yeah.
whereas inferencing, especially when you add on some RAG, can get into nickels and dimes. That
Mhm.
is a massive change, and it changes the whole potential business model. Can you be ad supported? Can you be this or that? So I do think this is potentially a game changer in terms of the cost of production alone.
Oh, absolutely. Yeah, it's a huge boon for builders, and it's largely a huge advantage for existing large scale inference cloud providers and things like that who are in the business of just hosting the models, right? And making it really cheap and easy to use them. Oh, okay. Harsh, I see there's a question, there's a chat. Okay, DeepSeek increase intelligence per dollar. Cheaper intelligence will not reduce the need for compute, but increase demand. Yeah, okay. So Harsh, I see there, I think this is another formulation of this idea of shifting the curve, which is like you spend more money and there's a function that converts that money into uh, intelligence. The curve shifting is just changing the slope of that line, which is what you're kind of representing here. And it's kind of the same thing as efficiency gains mean the same dollar input gets more intelligence output. And that's what we're seeing. And that's a trend that has been happening. Like I mentioned, that's not something that just suddenly happened. We just happened to see a step function change, and it happened to be open source, which are the two big takeaways. Um, I heard the story about one of the interview questions DeepSeek asked, were you committed to open source? Well, I'd rather believe there's some motivation around boosting the AI that can be benefit for all the people. Yeah, we're really just speculating about open source motivations at this point, but I think a lot of the open source community, there is a very, like, to be clear, AI has a huge open source community. And a lot of people are very motivated to make this like very public. And it almost boils down to like your core belief system at this point about like what you buy into. And I don't have a strong opinion. I'm not going to project that opinion on others. Any final
All right.
questions?
I checked LinkedIn. There's none there either.
Okay, cool.
Yes, so thank you so much, Corey. Thank you for coming out for the deep dive on DeepSeek on such short notice.
Yeah.
I know that everybody appreciates it, and you're getting a lot of thanks in the chat. Just a note to everybody who's joined us who hasn't taken the AI Product Manager course yet. If you enjoy Corey's teaching style, Corey is one of our instructors for the AI Product Management course. We're on our 9th cohort right now, and cohort 10 starts in April. So feel free to join us. We'd love to have you, and you can learn more about AI and in product management. Thanks again, everybody.
This is Haritha, and I am Director of Automation at Eversana. And in my past, I have seen AI projects, generative AI projects, but there was always some level of discomfort when approaching with questions to the engineers and architects, because just a lack of understanding of the technology. Well, I used to read online, learn some, do some self-learning, but it's hard to retain until you start putting something together on your own. And that's what the cohort helped us do is, introduce all the concepts, and we could go back and read more about it. Plus, applied immediately towards the end of the cohort. And that gave us much more confidence in talking to our engineers, our data people, and even trying to analyze a problem and see how a machine learning solution would fit in here. So huge shout out to Bijan and Kai for helping us in there. And I can personally vouch for this cohort because the kind of confidence that I got have now before compared to what I had before cohort is like night and day. I understand the concepts more. I know what I should ask my engineer. So highly recommend it.